SI.
Thank you, Dr. May. Another long title, sorry about that.
Yeah.
But I wanted to thank the entire CCQM organizing body as well as BIPM for accepting this contributed talk. Really enjoyed the week so far, and especially at a beautiful historic venue like this. So thank you very much, I appreciate it. So I'll share with you some of the work we're doing on the laser spectroscopy for accurate isotope amount determinations and isotope ratio determinations within the gas sensing metrology group at NIST. So of course, as we're all motivated by the pending agreed upon completed redefinition of the SI, I just wanted to share with you a little blurb from the NIST homepage that I think is going to be relevant for the rest of the talk here. And the idea is to try to make possible more accurate and precise measurement science anywhere in the world and even the universe without needing calibration to a specific artifact. So of course, spectroscopic approaches have the potential to be standoff and remote. So I think as we continue to look towards learning not only about the geology here on Earth, but also in other places in the solar system and potentially beyond, leveraging all of the wonderful information we can get from isotope ratios and isotope amounts with optical approaches is only going to continue to become more and more a part of our everyday life in this community anyway. So what does this completed redefinition of the SI mean potentially for the isotope and isotope ratio world? Where you see on the left are examples of the oxalic acid 1 and 2 standards that are used to underpin the radiocarbon dioxide scale, radiocarbon scale. How can we connect these physical artifacts with the new SI? As another example, I always like to share this story of, we saw the oxalic acid artifacts for radiocarbon. This is sort of the origin story for the PDB or Dee Belemnite reference material, which is used to underpin the delta 13 scale that Edgar introduced, as well as 018. And on the right-hand side here, you see Dr. Harold Urey, who went on an expedition with his colleague Heinz Loenstam down to South Carolina to actually mine the marine fossils that became the PDB sample. So I always like to think of Dr. Urey about 20 years after he'd already won the Nobel Prize on an excursion to get samples to bring back to the lab. And of course, these were measured at the University of Chicago by Craig on a Nairn instrument and really sort of pioneering measurements on that material. However, the question remains when we're working with artifact-based scales, if we run out of material, well, what could go wrong? And I like to share this quote from the Handbook of Stable Isotope Analytical Techniques. You know, there's considerable Babylonic confusion within the measurement community, which often perpetuates years after a new reference sample is introduced or a new 0 point is assigned to the isotope delta scale. Again, here particularly referring to PDB and Vienna PDB. So whenever there are potential, biblical consequences to what you're doing, it makes it a really interesting field to work in and try to solve problems. So, what is the absolute C13-C12 ratio for Vienna PDB, for the original sample, which is perpetuated now for close to 60 years as a sort of 0 point or origin point? Well, on the left-hand side here, you see the original measurement by Craig at University of Chicago on this sample brought back by Harold Urey and his colleagues. And you can see there's another measurement in 1990. Let's skip ahead here. Yeah, so the Craig value I can sort of jokingly refer to as the Wikipedia value. It's the one you're more likely to see if you just search for this value. It's still cited about once a day if you look at the Google citations. And later the IUPAC adopted this value that Edgar mentioned, which is from the 1990 measurements. And then since that time, there's been a whole host of additional mass spectrometry measurements trying to get at, again, not a delta value, but the absolute ratio of C13 and C12 in this reference material. What's important here is the error bars on this scale are not 0.01 per mil, but here they're about 1 per mil, or 1 part in 10 to the minus 3 is the uncertainty in this value. Again, the absolute ratio in the reference material. So this is an area where we think maybe we can make a contribution. So as Edgar nicely introduced, these measurements are generally made on a delta scale, so you're trying to get that C13, C12 ratio in your sample, which would be our sample in the top right equation there, further ratioing that ratio against the reference material, right? So you take a mass spectrometer, you measure your sample, measure the reference material, take the ratio, and express it on this delta scale. So what you see on the left is a plot of, on the y-axis, delta values on a Vienna PDB scale versus a mole fraction of C13 on the x-axis. So as you can see, for the range of delta values that's reasonable for terrestrial and atmospheric samples here on Earth, from, as Edgar pointed out, about +5 to -50, the delta scale is reasonably linear versus mole fraction. So you see in the bottom, I've just plotted residuals from a linear fit, and we're talking deviations of less than 0.01 per mil, so well under any measurement precision. But if you start to move slightly beyond that standard terrestrial range, from just having the mole fraction up to doubling the mole fraction, this has a huge change on the delta scale, right? Delta scale is designed to measure really small differences. But if you start to expand, you'll see that all of the x's are tight in that range. The x's represent the available reference materials. So now, just by having the bottom and doubling the top, we're into a range where reference materials aren't available, and the deviations from linearity are starting to get really large. So in the bottom plot, you can deviate by about 5 per mil at the edges here. It's about 1% of the delta value. So the point is that the delta scale, when you go beyond this comfortable region, is really nonlinear in mole fraction. And I think that makes a reasonable argument for why one might want to measure directly the mole fraction on an absolute scale instead of using delta values, especially when you start to think about tracer studies like in medicine or biology, where you might want to spike or enrich a sample and then trace that isotopic composition, as well as doing mass balance calculations and Keeling plots and things of that nature. So what can we do in the lab to try to measure mole fraction directly and translate mole fraction into absolute isotope ratios? Well, these are the types of questions we ask ourselves. You might say, should we even be asking ourselves these questions? But this is what we think about in the lab. Can we anchor ad hoc isotope scales and develop the metrology infrastructure for dissemination without using reference materials? You know, the accuracy goal here is going to be less than or equal to 1 × 10 to the -3. Again, that's on the order of the error bars in that plot I showed earlier. But we have to be aware and try to maintain a connection to the beautiful and exquisite precision you get when you're using the mass spectrometry techniques, when you're using these well-calibrated optical techniques. The accuracy we can project at this part in 10 to the -3 or maybe part in 10 to the -4 level is still a bit far away from the precision. So how do we bridge that gap? What applications is that useful for? You know, can we improve scalability, as I showed in the previous plot, beyond the available range of reference materials? And then maybe is it of interest to truly value assign as a community these legacy reference materials, hopefully before they disappear? So our technique that we're using is cavity ring down spectroscopy. So you see in this slide in the middle we have 2 gold mirrors which represent our highly reflective mirrors in our optical cavity. What the optical cavity allows us to have is an absorption interaction path length of approximately 10 kilometers on the bench top in about a 1 meter by 1 meter space. So we're talking about really high sensitivity, really high signal to noise. The cavity decay times are usually microseconds to hundreds of microseconds, things that are readily digitized in the laboratory. Importantly, in our instruments, we're never going to introduce a calibration gas. All right, we never calibrate our instrument response, which is a clear difference between using the high precision instruments and what we're trying to do. So briefly, how do we go from an exponential decay to a measurement of absorbance? Well, we get from the high finesse cavities very pure exponential decays, which we can fit to retrieve the time constant tau. As we tune our laser across an absorption feature, you can see here a CO2 line. We get time constant as a function of frequency. So we're measuring time, we're measuring frequency, and ultimately that's proportional to, or that can be related to an absorption coefficient alpha. If you prefer to work in transmission space, you can see in the bottom the conversion between alpha and transmission. And what we can take that fitted spectra, we can take the area under that absorption curve, so that would be the integral of alpha nu there. The area under that curve is proportional to the number density, and the proportionality constant is the inverse of the line intensity. So the line intensity is going to be the topic of the next portion of the talk. But the outcome here is the number density of absorbers. So as I mentioned on the previous slide, what we're going to need to know in order to get accurate number densities is the line intensity. Yeah? The inverse of the line intensity is the proportionality constant that we must know accurately. This is related to the cross-section that Joe was talking about earlier. But importantly, the line intensity is proportional to the transition dipole moment. And that's an invariant of nature. So just as for the dissemination of time or the definition of time, you can use an atomic frequency as an invariant of nature. Here we're just looking at the y-axis instead of the x-axis as our invariant that we're going to try to scale our technique by. So as Joe was able to introduce earlier, this concept of using an absorption cross-section to give you accurate number densities has been around for quite some time. This is very much the same thing as what Joe mentioned in the ozone cross-section. One of the key differences here is that instead of looking at this sort of blob of a cross-section, we're looking at line-by-line spectra, which are much more amenable to calculation from first principles. So what we're looking at is a rotationally resolved transition with one ground state and one upper state. So what we've done in the laboratory in the past is measure these transition dipole moments with traceability to the quantities that you see here in the laboratory. Again, no calibration. So trying to get an accurate measure of these invariants of nature. And then when we go in the lab and try to leverage those invariants to tell us absolute mole fractions and ultimately absolute ratios, we have to make, additional measurements of frequency, time, temperature, and pressure. Yeah, but all of these things through primary and secondary standards at NIST, we can trace back to the SI. We also have to understand the quantum mechanics of the gas phase molecules. We can readily do that and relate things back using invariants of nature and so on and so forth. So what's an example outside of this isotope ratio community where accuracy in these transition moments is really important? Well, this is a first map from the Orbiting Carbon Observatory, which is sort of showing the Earth breathing, essentially. So any bias in the transition intensity will directly map into a bias in the mole fraction of CO2 in the atmosphere in this measurement, because OCO is using spectroscopic reference data to extract mole fraction. This is very much the case for upcoming active LiDAR missions in CO2, the ASCENS mission. This is very much the case for the upcoming methane Merlin mission, joint French-German mission. So this is sort of pervasive. How well are we doing? Well, within the last year or two, we've shown within Joe Hodges' group that we can measure these intensities to better than 0.5%, so reasonably good. And within the last couple months, we've shown we can do even better than that. So currently our record right now is about a little less than 0.1%. All in all, in the past year or two, that amounts to about a 20-fold improvement over what's in the literature. So we're doing quite well. And we're starting to reach this part 10 to the minus 3 target. One application where we've built an instrument, I've talked a lot about C13. I also want to introduce C14 here. So we built an optical instrument for measuring absolute number densities of C14, radiocarbon dioxide. And we did that by building a really low temperature cavity ring down instrument. That reduces the Boltzmann factors of all the interfering lines nearby and lets us look at a select C14 transition. And we probed that in the mid-infrared. This sort of optical technique was first demonstrated by Galli and his colleagues at INO in Italy. They were using a highly nonlinear optical technique, where here we're doing linear absorption spectroscopy, so we're leveraging Beer's law, just as was described earlier. What you see on the left is our measurement of a biogenic sample of CO2, of neat CO2, and you can see the little shoulder peak on the left-hand side there is the signature of C14. So we also have a pair of C13 peaks nearby, which are reduced in temperature because of the instrument design. But the area under that C14 peak, just as we learned earlier, is proportional to the number density. So we were able to do that measurement on 2 different samples, one of biogenic origin and another of petrogenic origin. So the petrogenic sample is completely depleted in C14, and we can clearly distinguish between the 2 samples, as you see on these probability distribution functions. The cavity ring down measurement we made for the biogenic sample was about 0.75 fraction modern, so that's 75% of the nominal 1.2 parts per trillion of C14 that's in a neat sample of CO2. So we're looking at parts per quadrillion levels of C14 CO2. It's compared well with the with the accelerated mass spectrometry measurement, which we use as a baseline data point. So we're about 1 sigma away. Interestingly, this was supposed to be an entirely biogenic sample, and its fraction modern is a little less than 1. But that's backed up by the AMS community. So already we're able to distinguish at least between petro and bio, and there's a number of interesting applications related to measuring biofuel blends, bioplastics, where it's really sufficient to just be able to distinguish between 1 and 0 almost in many cases. So, all right, if I can wrap things up here in another slide or 2, what we've got plotted here are all of these isotopologues of CO2 that Edgar introduced with this numerical description. So this is the relative abundance on the top left. You see the 626. And you'll notice that 646 isn't on this chart. So 646 would be somewhere down here. It's another 4 orders of magnitude. All right. So, the easy thing to say is, well, the rest is easy, right? If we can see C14. Of course, that's not exactly true, but in terms of sensitivity, it's possible. Yeah, that's the take-home point. So really recently, we've been doing a lot of work on absolute isotope ratios of C13, C12, and the data we have really recently is that we think we can get those absolute amount ratios, and we can do it with per mil accuracy and with sub per mil measurement precision. So about 1/10 of a per mil in terms of measurement precision, and really honing in on that high accuracy in this case. So I'll just close here in the last minute or 2. Programmatically in our group, where do we think this whole picture might fit in? Well, with the optical transition intensities at the bottom here, we're really making connections between quantum chemistry calculations. There are theoreticians who can accurately predict these intensities to actually better than 1%, approaching 1/10 of a percent. So that's really powerful for, again, sort of exoplanetary atmospheres. That's what the theoreticians are really interested in trying to calculate the intensities for. But we're making strides comparing with CO2. And what we're talking about today is measuring isotope amount ratios. So what we envision doing at NIST is using in the bottom right our IRMS capabilities, potentially creating isotopic reference materials or collaborating with those in the community who are already doing so, linking that with our optical intensities, and really starting to be able to nail down some absolute isotope amount ratios while maintaining high precision from using IRMS. We can think about this a bit further if we start to, again, connect the intensities through cavity ring down, and we're talking about radioactive nuclei. C14 is a radioactive nuclei. We can actually start to think about doing absolute radioactivity measurements, and there are folks within the radiation divisions at NIST that are really interested in that. And going one step further, if we start to connect that back down to the isotopic reference materials, now we really have this interaction between absolute radioactivity, absolute gas counting, gas number densities on the radionucleotide side, as well as the stable isotopes. So we think there's a ton of connections here just within NIST, and I'm sure that many of these connections are also out there across working groups here at the CCQM. So I'll thank our group. This is part of our group that's mainly focused on the laser side in gas sensing metrology. I want to thank the folks at NIST who have funded much of this work, the Innovation Measurement Science Program, Greenhouse Gas and Climate Science Program, and also some funding support from the NASA Orbiting Carbon Observatory. So thank you for your time.